All right, welcome back. We're going to go ahead and complete a full-on hypothesis test for the ANOVA procedure. So we have our summary here, and we'll kind of go through it as we work through this. But I really do want you to memorize the requirements. Oh, I just see that this is not numbered properly. I want you to memorize the requirements because we will need to check these for each group. All right, so here's our first example. The results of a comparison of 4 popular minivans are reported in the following table. What they were looking at here was the braking distance. So this is the number of feet required for the minivan to come to a complete stop when it went from 60 miles per hour to full-on brakes. And again, this is a fairly important because if you have a minivan, you're probably in need of a minivan and potentially drive a lot of individuals. So braking distance, this would be fairly important. All right. And again, we have this across different minivans. So minivan A, it just says minivan A. It could be different brands. So for example, this could be a Toyota. Toyota, I don't even know what the brands are, but then this could be a Ford, if they make a minivan, I don't know. Toyota, Ford, maybe a Mercedes, one of those like passenger vehicles. And again, you kind of get the point. We have group 1, group 2, group 3, group 4, and we have a quantitative variable, which is braking distance. So the question is there a difference across these different groups? So let's go ahead and just start by answering the following. Is it possible that each group comes from the same distribution? And again, this was the whole purpose of the previous video, to try and build the intuition. Here we have the braking distance. So here's my random variable on the x-axis. And then I have the braking distance according to the group. And I'm going to go ahead and right away say that no, it does not look like all of the data here comes from the same group, because we can see that minivan D is very different. All of these braking distance are much higher. So that's this one, 160, versus all the other ones. They're between 150. Yeah, they're in the 150. And so there's overlap here in these. These values overlap. Again, if you were to look at them all on the same axis at the bottom, there's a lot of overlap versus this one here. This one, this one's potentially different. All right, so let's go ahead and actually go through all of the requirements here. So let me carry out this procedure. I already have an idea of what should happen, so let me go ahead and start with number 1, which is let's write out the hypothesis. So always write out the hypothesis. You can either, here it is. My null hypothesis is that all means are equal. If this is the easy way to go, or you can go ahead and write that mu A. So the average for A is the same as the average for B, same as the average for population C, same as the average for D. And we're going to go ahead and compare that to the alternative, which is that at least one mean is different. So my null hypothesis is that all means are the same. The alternative is that they are not the same. Now let's go ahead and check the requirements. So this is the first time that we've seen them. Here are the requirements, and 1 through 3 are actually not new. So these we've seen before. So the way that I like to think about them is that you want to check that every sample that you get, so the results from minivan A, minivan B, minivan C, and D, that those are separate different examples. So that's fairly simple to assume. You can go ahead and assume that, it's SRS. So requirement 1, SRS. We're going to check it off for each. Requirement 2, that's independence. And remember that this basically says that group 1, so 1, 2, 3, 4. So the number of samples in group 1 is 4, and that's the same as the number of samples in the rest of the groups. And remember that independence we basically get by saying, is that sample independent from the pot amongst themselves? And the way that we verified that was that the sample size is small relative to the population. So it's less than 5% of population one. So however many minivans there are from group one, we have less than 5%. And again, that's going to be safe to assume for every group. So I'm just going to write it as Ni is less than 0.05 of big of Ni. So sample size I is less than 5% of the population I. So 2 is met. And then finally, the last one, populations are normally distributed. So each population is normal. And this is the one that we verify. Either you have large sample size is greater than or equal to 30, or you check normality, that the population that you're looking at, so xi, is approximately normal. And so that's what we did for the previous section as well. So let's quickly go ahead and say that. Notice these don't really look normal, and I have a very small sample size. So I need to go ahead and check QQ plot and box plot. So to do that, I need to first get this data. And luckily, we have the data shared in our group. So if you go to a group, you should be able to access the data in 4.3, I believe. Yeah, so we have our notes right here, ANOVA. All right, so I'm going to go to graph, and I'm going to go ahead and create box plot for A, B, C, D. So there are my box plots. Notice there's no outliers. And then I'm going to go ahead and create QQ plots for A, B, C, D. And remember, we want to add the correlation statistic and the normal quantile so that we can see the correlation coefficient. So there's correlation 1, correlation 2, and correlation 3. Oh, and correlation 4. We can see them all on the same by changing this to number of rows. Let's make that 4. All right, and now we can see the correlation here for minivan A, correlation for minivan B, correlation for minivan C, and minivan D. So we need this information to argue that, hey, these are actually normal, that the population is normal. So let's go ahead and say box plot shows no outlier. And then give me the correlation for each one. The correlation coefficient for A is 1. Correlation coefficient for B was 0.9. So I need to go grab it. 975. For C, it was 945. And for D, it's 994. So the red information right here, because the box plot, I do not have an outlier and I have a significant correlation coefficient here. Both of these right here mean that there's evidence that each population is in fact normally distributed. Okay, so that's the same check that we had before. So notice I've gone through 1, 2, 3. Finally, we need to go ahead and check whether we have approximately equal variance. And this is all new, so let me emphasize this. So approximately equal variance. What that basically tells me is that the variability from group 1, group 2, group 3, and group 4 should be about the same. So here we're basically assuming it's a hypothesis test within. So it's saying the variance 1 is more or less the same as variance 2, same as variance in group 3, population 3, and variance in population 4. So is this true? And there's 2 ways to do this. Let me just go ahead and show you how we can meet this requirement with the equal. So this is called the equal variance assumption. ANOVA still works if this assumption isn't really held, but I want you guys to just test this using what's called the Levine test or the Brown-Forsyth test. Okay, so this is to check requirement 4. So notice there's requirement 1, requirement 2, and requirement 3. And so for requirement 4, we need to do a hypothesis test. We're going to go ahead and start by saying, let's check whether it's true. Let's assume that the variances really are equal to each other. Then the alternative would be that at least one of the variances is different. So we're going to do a hypothesis test. And here, the hypothesis test, we're simply going to look at it by using the p-value. So to complete this hypothesis test, you're going to go to Stats. And remember, this is a test on the variability. And then go to Variance. And select Homogeneity. This basically says that homogeneity means equality. So are the variances equal? Then you look at the p-value. And the logic will be the same. So again, if the p-value is small, so let's say that if that's less than 0.05, then you reject. You're going to reject the null hypothesis because you have an unusual sample. But if it's greater than 0.05, you fail to reject. And it sounds weird, but in this case, you want to fail to reject. Why? Because if you fail to reject, then you're basically saying, I have evidence to support the null hypothesis, which is that the variances are equal to each other. Okay, so in this case, you actually want to be greater than 0.05. Let's just go ahead and carry this out. I have my data, and I'm going to go to Stats, Variance, Homogeneity. Stats, Variance Stats, Homogeneity. Select all 4 columns, A, B, C, D, and then just leave it alone. Just select where it says Levine test. You can change it if you want to Brown-Forsyth. Levine is one of the standard ones, so we'll leave it there. And then you press compute. And here you have the results for your homogeneity of variance results. So are the variances equal in those different data sets? Here's your test statistics, so we don't got to worry about this stuff. And here's your p-value, 0.04. 0.4087. And again, the fact that this 0.4, so this result happens 40% of the time, means that we go to that's greater than 0.05. We fail to reject the null, so we support the null hypothesis. So we're going to go ahead and say we can assume that the variances are equal by the Levine test. So by the Levine test, it's safe. So we have evidence to say that the variances are equal. Which is kind of strange because if you look at the variability here, the variability in A is actually very small versus B versus C versus D. So the variability is increasing, but this test is actually very robust in the sense of you have to exhibit extreme differences in order for this test here to be rejected. So that's part of the reason why it's the go-to. This seems like a lot of work, so I'm going to give you guys an option. You can either do this test, or you can do what's called a rule of thumb, which just says, well, is there a different way? Why this is fairly involved. I never told you what the test statistic is or what the distribution is. So a lot of times people use the rule of thumb, which says we're going to assume that the variances are equal if, so either you do a Levine test or you check whether the largest standard deviation is less than twice the smallest standard deviation. So let me go ahead and find that we actually don't meet it with this requirement. So again, there's 2 ways to do this. You do it using 1 or 2. Okay, so that's for 4. Let me show you this one just real quick. Largest standard deviation has to be smaller than double the smallest of the standard deviations. So the way I would do that is I would just go to summary stats for these columns, A, B, C, D. And really, I just want the standard deviation. So if I look at this standard deviation, the standard deviation in A is 1.29, in B is 2.64, and C and D. And then we basically say, what is the smallest? Look at it long enough until you realize, or you're okay with the statement here, that the smallest is this one. And then the largest standard deviation, look at this long enough, 2.6, 3.55, 3.10 is this one, 3.5. $3.559. And then you check whether the largest, so basically just take the easy way to do it is you want to double the smallest one. And so that would be 2 times 1.29. That's roughly 1.3. So this will be roughly 2.6. I don't really care about the answer. And then what I want to meet the requirement under this assumption, all other standard deviations have to be less than 2.6. Notice that that doesn't hold here. So it works for this guy, it works for this one, but it doesn't work for these. So if you just simply use that rule of thumb, unfortunately for our data set, you would not be able to proceed with the test. And so unfortunately, this rule of thumb fails for this data set. So the data does not hold in this scenario. And so it would seem like you cannot do a ANOVA test on this data set, but that's wrong. Because again, if you use a more robust test, so let's clear our drawings. If you use a more robust test like we did here using the Levine test, we find that we actually do have evidence to say that the variances are equal. All right, that's pretty much it. This takes a lot of time, again, checking the requirements. But again, the first 3 you've already done. The 4th one is new, and that's a new hypothesis test to check whether the variances are equal, or you can just use the rule of thumb. I recommend you use the Levine test because it's actually easy to find. And let me go ahead and show you guys why. Let's finally perform the ANOVA test. And the ANOVA test, let me go ahead and do it 2 ways. You really only have to do this 1 way. Let me do it using the F statistic. With the critical value, and then I'll show you with p-value. With p-value is by far the easiest. You only have to do 1. If you're going to do this with the critical value, then you got to go ahead and produce your sketch first. You got to say, well, here's your F distribution. Let's go ahead and leave this at a 0.05 significance level. And then I'm interested in what is the F statistic? What is F sub alpha? Sorry, the critical value, F sub alpha. Let's find that first. And the way that you do that is you can just simply go to ANOVA. So let's go to stats. ANOVA, there's a 1-way ANOVA because we only group by 1 variable, the vehicle type. Select your columns, and that's pretty much it. Notice that you could have done the test for homogeneity in this little tool here. But anyway, we are going to go ahead and use the ANOVA function, select our data, press compute, and you have all the information that you need. So you have your F statistic here, 23. And notice that that statistic is huge. It's 23. Remember that the way this works is you're looking at the so your F statistic is the MST over MSE. So the mean squares due to treatment over the mean squares due to error. So notice the columns here tells you how many different groups you had. You had 4 groups, right, for different categories. So categories were 4. And that's why there's 3 degrees of freedom, because you're subtracting 1. And then the error, basically, you go ahead and say, well, how many different data points were there? And then you go ahead and take your data points and you go ahead and subtract the number of columns that you had. We're not going to do this by hand, so just go ahead and read this. Degrees of freedom on top is 3. Degrees of freedom on the bottom is 12. Because remember, it's this. So that's the degrees of freedom. Here's the sum of squares due to treatment. It's 534. Sum of squares due to error. That's 93. And then you simply divide these numbers. So 93 divided by 12 is roughly 7.75. And then 178, or sorry, 534 divided by 3 is roughly 178. So these here are the MST, and so here's MST, and here's MSE. I'm never going to ask you guys to compute this by hand, so you're always going to be able to use technology to find them. Then you just divide them. You take MST divided by MSE, and that gives you the F statistic. So it's more or less the way it's already here, 178.25 divided by 7.75. That gives you 23. So notice that what you're saying is that the variability across the groups, 178.25, is around 23 times as large as the variability within the groups. So when I explained it in the previous video, this was the green. So this is the variability in green. So that length is very high, 178. And then the red is MSE. So that's 7.75. That's the variability within the groups. And that's very small like this. So it says that within the groups, there's almost no variability when you compare it to the variability across the different groups. And so the green length is more or less 23 times as large as the red length. So that means that there's a large variability due to the different groupings. So there is a difference in the groupings. We knew that already. Okay, so anyway, let me just wrap this up. Let me find this critical value. So we go to stats, calc, F. And remember that the degrees of freedom were 3 and 12. And I want the area to the right to be 0.05. So my critical value is 3.49. And I don't actually need to do this because I already know that the F statistic is so large. It was 28. It's all right. 23, sorry. So what this says is, hey, you definitely have you got to reject this, right? Because here's your sample. So that's the F statistic that we get. So we reject. All right, I don't recommend that you do it this way because it takes a lot of work. I recommend that you do it using the p-value. So it'll be easy, kind of like the Levine test. So just simply read the p-value off of your ANOVA output. My p-value here is tiny. It's less than 0.0001. In other words, that's less than alpha. So again, that tells you that you land in the tail. You have a very unusual result. So because of that, you're going to reject age 0. And the null hypothesis that we're rejecting is the original null hypothesis, that the means are equal. So we're rejecting the null hypothesis, so I can cross this out. There is no way that the means are actually all the same. We're finding evidence against that. And it did not take a test for me to say this because I had already said that this last group is very different from the other 3. So the group that I think is different is going to be group D. And we would need additional statistics for this, but we'll just stop here. That's the ANOVA test on this example. So go ahead and rewatch this. So let me finish this. You reject the null, and we're going to say we have sufficient evidence at the 5% significance level that to support the claim or to say that not all mean braking distances are equal, or that, yeah, not all means are equal. Mean braking distances. And there we have it. We have our first full hypothesis test for the ANOVA procedure. Go ahead and rewatch this. There's a lot going on. I'm going to go ahead and do one more sample. And I want to just emphasize that you want to write the hypothesis test, check the requirements. There's 4 of them. It takes a long time. You're probably going to have to do a Levine test here for equal variances. So that's new. And then finally, at the end, we go ahead and just simply use the p-value. Try not to sketch as it takes a lot longer. So we'll just use the p-value for this last part. All right, thank you for joining me. If you have questions, make sure that you reach out, and I'll see you in the next video.